Welcome! In this session, we'll explore an interesting and challenging problem titled Shortest Distance from All Buildings. This problem is a great exercise in algorithm design and optimization, touching on topics like breadth-first search, BFS, and grid traversal. Let's dive in and break it down step by step. In this problem, you are given a grid, represented as an MXN 2D list, where each cell in the grid can be one of three types. 0 represents an empty land cell where you could potentially build a house, 1 represents a building, and 2 represents an obstacle, which you cannot pass through. Your task is to choose an empty land cell to build a house such that the sum of the shortest distances from the house to all buildings in the grid is minimized. You can only move in 4 directions: up, down, left, or right, and you cannot travel through cells marked as obstacles. If no empty land cell satisfies this condition, you should return -1. The input for this problem is the grid itself, and the output is an integer representing the minimum sum of shortest distances, or -1 if no valid solution exists. Let's consider an example to understand this better. Suppose the grid is as follows: 1, 0, 2, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0. This grid contains 3 buildings located at positions 0, 0, 0, 4, and 2, 2. Your goal is to determine the best possible location to build a house, minimizing the sum of shortest distances to all 3 buildings. In this case, the optimal location for the house is at position 1, 2. The shortest distance from this position to each building is as follows: to 0, 0, the distance is 3, and to 0, 4, the distance is also 3. From the same optimal location, 1, 2, the distance to the building at 2, 2, is 1. Adding these distances together, you get a total distance of 3 plus 3 plus 1 equals 7. Therefore, the output for this example is 7, as that is the minimum sum of shortest distances from the house to all buildings. Now, let's look at another example. Consider the grid 1, 0, 0, 0. Here, there is only one building located at 0, 0. The best location for the house is at 1, 0, which is directly adjacent to the building, resulting in a shortest distance of 1. Thus, the output here is 1. Now, let's explore a case where it is impossible to build a house. Take the grid 1, 2, 0. In this grid, there is one building at 0, 0, and one obstacle at 0, 1. The only empty land cell is located at 0, 2. However, it is not possible to connect this empty land cell to the building while avoiding the obstacle. As a result, there is no valid location to build the house, and the output for this example is -1. This demonstrates how obstacles or grid layout can make it impossible to find a solution. Finally, let's review the constraints and edge cases for this problem. The grid dimensions m and n are both between 1 and 50. There is guaranteed to be at least one building in the grid, and all cells will contain only the integers 0, 1, or 2. Some edge cases to keep in mind include: if the grid contains only one cell, it must be a building; if all cells are obstacles, the output should be -1; if no empty land cells exist, the output is also -1. Additionally, if buildings are isolated by obstacles, making it impossible to connect to them, the output should be -1. The constraints ensure that the solution can be computed efficiently, even for the largest grids, with a time complexity on the order of O(m*n*k), where k is the number of buildings. To solve this problem, we start by examining different approaches. The brute force approach is intuitive but inefficient. Here, for every empty land cell in the grid, we calculate the sum of distances to all buildings. This is done by performing a separate BFS or DFS for each empty land cell, which ensures we find the shortest paths, but at the cost of high time complexity. Specifically, in the worst case, we could end up with a time complexity of O, open parenthesis m times n close parenthesis squared, where m and n represent the dimensions of the grid. Additionally, the space complexity is O, m*n, which accounts for the Q used in BFS. While simple, this method becomes impractical for larger grids due to the sheer number of redundant computations. To address this, we consider an optimized approach. Instead of focusing on empty lands, we reverse the calculation and focus on the buildings. From each building, we perform a BFS to calculate distances to all reachable empty land cells. During this BFS, we maintain two key arrays: a distance array that accumulates the total distance from all buildings to each empty cell, and a reach array that tracks how many buildings can reach each cell. This approach minimizes redundant computations by shifting the focus to buildings, which are fewer in number compared to empty land cells in most cases. Once the BFS is completed for all buildings, the next step is to identify the optimal empty land cell. For this, we iterate over the grid to find the cell with the smallest cumulative distance in the distance array, provided that the cell is reachable by all buildings. This is verified using the reach array, where the condition reach, j, equals total_buildings ensures the cell is accessible from every building. If no such cell exists, we return -1, indicating that it's impossible to find an optimal location. This approach is efficient because it avoids redundant computations for empty cells, leveraging the fact that BFS inherently calculates the shortest path. Moreover, the reach array simplifies the process of verifying accessibility for all buildings. The time complexity of this approach is O(m*n*b), where b is the number of buildings, as we perform a BFS for each building. The space complexity remains O(m*n), accounting for the distance and reach arrays, as well as the BFS queue. While BFS is sufficient for this grid-based problem, alternative methods like Dijkstra's algorithm or A*search can also be considered. However, these methods add unnecessary complexity without yielding significant benefits, as the grid's uniform edge weights already make BFS the most straightforward and effective choice. The strategy we've chosen is the optimized BFS-based approach. This method stands out because it eliminates redundant calculations by focusing on buildings instead of empty lands. By performing a single BFS for each building, we efficiently compute cumulative distances and track reachability, aligning perfectly with the grid structure. This approach strikes an ideal balance between simplicity and performance, making it practical for real-world scenarios. In comparison, while the brute force approach is conceptually simpler, its poor scalability renders it unsuitable for larger grids. On the other hand, advanced algorithms like Dijkstra or A** add unnecessary complexity without providing meaningful improvements, as BFS already handles the problem efficiently given the grid's characteristics. Ultimately, the optimized BFS-based approach offers the best trade-off between simplicity, performance, and clarity, making it the most effective solution for this problem. In this problem, we're working with a 2D grid where the cells can be one of three types: a building, represented by a 1, empty land, represented by a 0, or an obstacle, represented by a 2. Our objective is to determine which empty land cell minimizes the total Manhattan distance to all the buildings in the grid. The Manhattan distance, as you may recall, is the sum of the absolute differences of the row and column indices between 2 points. If it's not possible for any empty land cell to reach all buildings, the function should return -1. This problem is challenging because we need to efficiently calculate and compare distances for potentially many cells while accounting for obstacles that can block paths to buildings. To solve this problem, the algorithm begins with pre-processing the grid. First, we parse the grid to identify the positions of all buildings, which are the cells with a value of 1. As we do this, we also keep track of the total number of buildings, referred to as number_buildings. This count will be crucial later to verify that all buildings are reachable. Next, we initialize two additional 2D matrices, distances and reach_count. The distances matrix will store the cumulative Manhattan distance from all buildings to each empty land cell, while reach_count will track how many buildings can reach each empty land cell. With this setup in place, we then perform a breadth-first search, or BFS, starting from each building. The BFS will systematically explore all reachable empty land cells, updating the distances and reach_count matrices as it traverses the grid. To manage the BFS process, we use a queue that stores tuples containing the current cell's coordinates and the distance from the building. Additionally, a visited matrix ensures that each cell is processed only once per BFS run. During the BFS traversal, the algorithm incrementally updates the distances and reach_count matrices for each empty land cell. If a neighboring cell is empty land and hasn't been visited yet, its distance is incremented by 1, and the reach_count for that cell is also updated to reflect that it is now reachable from another building. The algorithm skips any cells that are obstacles or other buildings since they cannot be traversed. Once the BFS for a building is complete, we ensure that all reachable cells have been processed. With the BFS phase done for all buildings, the next step is to identify the best empty land cell to minimize the total distance. To do this, we iterate over all grid cells and look for the smallest value in the distances matrix where the corresponding reach_count matches the total number of buildings. This ensures that the chosen cell is reachable from all buildings. If no such cell exists, meaning there's no empty land that can reach every building, the algorithm returns -1. Otherwise, it returns the smallest cumulative distance found. BFS is a key part of this algorithm because it efficiently calculates the shortest paths from a building to all reachable cells. By exploring level by level, BFS avoids unnecessary or redundant paths, making it ideal for grid-based problems like this. Tracking the reach_count matrix is equally important since it ensures that the solution only considers empty land cells that all buildings can access. Without this, the algorithm might incorrectly prioritize cells that are unreachable from certain buildings. Pre-computing the positions of all buildings at the start of the algorithm is another optimization. It eliminates redundant calculations and speeds up the initialization of the BFS process. The algorithm also accounts for edge cases, such as when no empty land is reachable from all buildings, or when the grid is composed entirely of buildings and obstacles. It's robust enough to handle grids of varying dimensions, whether they're very small or very large. The algorithm uses several data structures to achieve its goal efficiently. The grid matrix itself is the input, representing the layout of buildings, empty land, and obstacles. A queue is essential for managing the BFS process, allowing cells to be processed in the correct order. 2D arrays, distances and reach_count, are used to store the cumulative distances and track how many buildings can reach each empty land cell. These arrays provide O(1) access time for each cell, which is crucial given the problem's constraints. When analyzing the complexity, the time complexity of the algorithm is O(B*M*N), where B is the number of buildings and M and N are the grid's dimensions. This is because BFS is performed for each building, and each BFS can explore up to all grid cells. The space complexity is O(M*N), which accounts for the BFS queue, the visited matrix, and the 2D arrays. Overall, the algorithm is designed to handle the problem efficiently within these constraints. Finally, the algorithm returns the minimum cumulative distance from an empty land cell to all buildings. If no such cell exists, meaning there is no empty land that is reachable from every building, the algorithm returns -1. This ensures that the output is either the optimal solution or a clear indication that no solution is possible given the grid's configuration. Here, we start by importing the D class from the Collections module, which will help us implement a breadth-first search or BFS. Inside the solution class, the shortest distance method takes a grid as input, representing the city layout. We first determine the number of rows and columns in the grid, and then initialize two matrices, total_distance to track the cumulative distance from empty land cells to all buildings, and reachable_count to count how many buildings each empty land cell can reach. Additionally, we calculate the total number of buildings in the grid by summing up all cells with a value of 1. Next, we define a helper function BFS to perform a BFS starting from a specific building located at start_o and start_call. This function uses a queue to explore neighboring cells, tracking their distances from the starting point. For every valid neighbor that is an empty land cell, we update the total_distance and reachable_count matrices, and mark the cell as visited to prevent reprocessing. After updating the necessary matrices, the cell is added to the queue to continue exploring its neighbors. This ensures that we propagate distances level by level from the current building. Finally, we initiate the BFS process for each building in the grid. If a cell is identified as a building, we call the BFS function on it to calculate its contribution to the total_distance and reachable_count matrices. Once the BFS has been executed for all buildings, we need to determine the minimum distance from an empty land cell to all buildings. To do this, we initialize a variable result with infinity, which will store the smallest distance we find. Then, we iterate over every cell in the grid. If a cell is empty land, and its reachable_count matches the total number of buildings, it means this cell can access all buildings. In such a case, we update result to be the smaller value between its current value and the distance stored in total_distance for that cell. After processing all cells, we return the result as the final answer. If no empty land cell can reach all buildings, the result remains infinity, and we return -1 instead. This ensures we handle edge cases where it's impossible to find a valid solution. Together, this implementation efficiently calculates the shortest distance from all buildings to an empty land cell using BFS and dynamic programming concepts. Here, we begin implementing the solution in Java. First, we import the necessary packages and define the solution class. The main method, shortest distance, takes a 2D grid as input, which represents the map where 1s are buildings, 0s are empty land, and 2s are obstacles. We initialize variables for the number of rows and columns, as well as 2 auxiliary matrices, total distance, and reachable count. These will help us track the cumulative distance from buildings to each cell and the count of buildings reachable from each cell, respectively. We also initialize a buildings counter to keep track of the total number of buildings in the grid. Next, we iterate over every cell in the grid. When we encounter a building, we increment the buildings counter and call a helper method BFS to perform a breadth-first search from that building. This BFS updates the distance and reachability matrices for all reachable empty land cells. After processing all buildings, we loop through the grid again to find the minimum distance to all buildings from any empty land cell. If a cell is empty, reachable by all buildings, and has the smallest total distance so far, we update the result. The goal here is to ensure that we find the optimal cell or return -1 if no such cell exists. After completing the grid traversal, we return the result. If no empty cell satisfies the condition of being reachable from all buildings, the result remains integer.max_value, and we return -1. Otherwise, we return the computed result. Now, let's look at the helper method BFS. This method performs a breadth-first search starting from a specific building. It takes the grid, the starting row and column, and the distance and reachability matrices as arguments. We initialize a visited matrix to track cells we've already processed during this BFS traversal. We also use a queue to manage the BFS, starting with the building's location and an initial distance of 0. While the queue is not empty, we process each cell by dequeuing it and checking its neighbors. For each valid neighbor, those that are within bounds, not visited, and are empty land, we mark it as visited, update its distance in the total distance matrix, increment its count in the reachable count matrix, and enqueue it with an increment distance. This ensures that all reachable cells are properly updated as the BFS expands outward from the building. Finally, we close the BFS method by ensuring all neighboring cells are processed. The inner loop iterates through the 4 possible directions up, down, left, and right and calculates the new row and column indices for each direction. If the new position is valid, meaning it's within the grid, hasn't been visited, and is empty land, we proceed to update the visited status, accumulate the distance, and increase the reachability count for that cell. This ensures that every step taken from the building is accounted for in the distance calculation. By the end of the BFS method, all reachable empty land cells from the starting building will have been updated in both the total distance and reachable count matrices. This completes the process of propagating distances from a single building, which is then repeated for all other buildings in the grid by the main method. With this approach, we ensure that the solution is both efficient and adheres to the constraints of the problem. Here, we begin with a basic example to understand the solution. The input grid contains 3 buildings, represented by the value 1. The dimensions of the grid are 3 rows and 5 columns. We initialize total_distance and reachable_count as 3 by 5 grids filled with zeros. These will help us track the sum of distances from all buildings and the number of buildings that can reach each empty cell. The first step is to perform a breadth-first search, BFS, starting from the building located at 0, 0. During this BFS, we maintain a visited grid to ensure we don't process the same cell multiple times. Starting with a queue containing the building's position and distance 0, we explore its neighbors. For instance, moving to 1, 0, we calculate a distance of 1, update total_distance, 1, 0, to 1, and increment reachable_count, 1, 0, to 1. Similarly, for the neighbor at 0, 1, we update its total_distance and reachable_count as well, reflecting the distance and the fact that it's reachable from this building. Next, we perform BFS for the building located at 0, 4. Using the same process, we propagate distances to empty land cells and update the grids accordingly. Then, we repeat this with the building at 2, 2, ensuring that only empty cells reachable from the buildings are updated. Once BFS is complete for all buildings, we evaluate the results by iterating through all the empty land cells in the grid. For example, the cell at 1, 2 has reachable_count equal to 3, meaning it is reachable from all 3 buildings, and its total distance is 7. Therefore, the minimum distance from all buildings to an empty land cell is 7. This becomes our final output for this example. Now, consider a scenario where no empty land is reachable from all buildings. In this grid, there are 2 buildings, and obstacles with value 2 block the paths to empty land cells. After initializing the total_distance and reachable_count grids, we perform BFS starting from the building at 0, 0. Due to the obstacles, no empty cells are reachable, so there are no updates to the grids. Similarly, for the building at 2, 2, BFS results in no updates for the same reason. Finally, when we check all empty land cells, we find that none has a reachable_count equal to 2, meaning no empty cell is reachable from both buildings. As a result, the output for this case is -1. In this example, the grid is smaller, with 2 buildings and 2 empty cells. After initializing the total_distance and reachable_count grids, we begin BFS from the building at 0, 1. This updates the distances and counts for reachable empty cells. Then, we perform BFS from the building at 1, 0, combining updates to account for cumulative distances. For instance, at the empty cell 0, 0, we find that it is reachable from both buildings, with a total distance of 2. As all empty cells are reachable from both buildings, we can determine the minimum distance from all buildings to an empty cell. Here, the result of the calculation shows that the empty cell at 0, 0 has the minimum total distance of 2 from all buildings. Since this is the smallest possible distance in the grid, the output for this example is 2. To analyze the time complexity of our solution, let's break it down step by step. First, there's the initialization phase. Here, we create 2 matrices, total_distance and reachable_count, both of which need to store values for every cell in the grid. Since the grid has rows*calls cells, initializing these matrices will take rows*calls time. Additionally, we determine the total number of buildings in the grid by iterating through every cell. This operation also requires rows*calls time. Next is the BFS traversal. For each building, represented as 1 in the grid, we start a breadth-first search to calculate the shortest distance to all reachable empty land cells, marked as 0. In the worst case, the BFS explores every unblocked cell in the grid, which could be all rows*calls cells. If there are B buildings, we perform this traversal B times. This means the total time spent on BFS across all buildings is B** rows*calls, making it the dominant component of the time complexity so far. Now, once all BFS traversals are complete, we still need to find the optimal meeting point. This involves iterating through the total_distance and reachable_count matrices to identify the cell where the total distance is minimized. Since these matrices have rows*calls cells, this step takes rows*calls time. When we combine all these steps, the overall time complexity is determined to be B** rows*calls, where B is the number of buildings in the grid. Moving on to space complexity, we begin by considering the auxiliary matrices total_distance and reachable_count. Both of these matrices require rows*calls space since they store values for every cell in the grid. Additionally, during each BFS traversal, we use a visited matrix to track which cells have already been processed. This matrix also contributes rows*calls to the space complexity. Another factor affecting space complexity is the queue used for BFS. As the algorithm explores the grid, it adds cells to the queue. In the worst-case scenario, the entire grid could be added to the queue, leading to a space usage of rows*calls. When we combine these factors, the auxiliary matrices, the visited matrix, and the BFS queue, the total space complexity of the solution becomes rows*calls. To appreciate the efficiency of this approach, let's compare it to a brute force method. With brute force, we would test each empty land cell as a potential meeting point. For every such cell, we'd perform a BFS to calculate its distance to all buildings. This would result in a time complexity of O, rows asterisk calls, asterisk B asterisk, rows asterisk calls, or O, B asterisk, rows asterisk calls, caret 2. In contrast, our optimized solution avoids redundant calculations by performing BFS from each building only once, reducing the time complexity to O, B asterisk rows asterisk calls. Now let's analyze the best, average, and worst case scenarios for our algorithm. In the best case, the grid contains only one building, and all other cells are empty land. Here, BFS will visit all cells just once, leading to a time complexity of O, rows asterisk calls. In the average case, the grid contains multiple buildings and obstacles. For each building, BFS explores a subset of the grid, giving us a time complexity of O, B asterisk rows asterisk calls, where B is the number of buildings. In the worst case, the grid is densely populated with buildings, meaning B is large. Additionally, BFS would need to explore all reachable empty cells for every building. Even in this scenario, the time complexity remains O, B asterisk rows asterisk calls. Finally, a mathematical proof of complexity confirms these findings. Each BFS traversal processes each cell at most once, contributing O, rows asterisk calls, per building. With B buildings, the BFS cost adds up to O, B asterisk rows asterisk calls. Since the initialization and final iteration steps also require O, rows asterisk calls, each, these are dominated by the BFS cost. Thus, the overall time complexity is O, B asterisk rows asterisk calls, and the space complexity is O, rows asterisk calls. When solving this problem, there are several mistakes you'll want to avoid. First, incorrect initialization during BFS or DFS is a common issue. If you forget to reset the visited states or fail to correctly initialize distances for each traversal, it can lead to inaccurate results. Always ensure that each search starts with a clean slate. Another common pitfall is overlooking edge cases, such as grids with no buildings, no empty land, or scenarios where connecting all buildings is impossible. Neglecting these can cause runtime errors or incorrect outputs, so it's essential to test thoroughly for these conditions. Inefficient brute force approaches are also a problem. Directly calculating distances for every empty land cell results in an O, n squared asterisk m squared, time complexity for an nxm grid, which becomes infeasible for larger inputs. Instead, focus on optimizing your solution. Additionally, misinterpreting problem constraints, such as confusing grid values or not accounting for unreachable buildings, can lead to faulty logic, so always review the problem statement carefully. Finally, boundary check errors during traversal are another common bug. Ensure any index you access stays within the grid's bounds to avoid unexpected crashes. Now, let's focus on insights that can be helpful in interviews. One key optimization is to calculate distances from the buildings rather than from empty land cells. By initiating BFS from each building and propagating distances outward, you reduce redundant computations and improve performance. While a brute force approach may seem simpler to implement, it's computationally expensive. The optimized BFS approach not only reduces the time complexity but also requires careful tracking of cumulative distances, which demonstrates a deeper understanding of the problem. This problem also highlights an important pattern, the use of multisource BFS. Recognizing when this technique applies is a critical skill, as it's often the most efficient way to handle grid-based shortest distance problems. During interviews, make sure to communicate your thought process clearly. Discuss any edge cases you've considered, explain the trade-offs between different approaches, and emphasize how you would validate your solution to ensure correctness. Finally, let's explore related problems and alternative approaches. There are several similar problems that can help you strengthen your understanding of BFS and grid traversal. For example, LeetCode 286, Walls and Gates, involves finding the shortest distances from gates to empty rooms. LeetCode 542.01 Matrix uses a multisource BFS to find the nearest zero for each cell. And LeetCode 847, Shortest Path Visiting All Nodes, shifts the focus to graph traversal with state and distance tracking. These problems share underlying principles with this one, making them excellent practice. When it comes to alternative approaches, starting BFS from all buildings simultaneously is a powerful optimization. This multisource BFS reduces redundant computations and achieves an O, and squared asterisk m complexity, which is much more efficient. For weighted grids, Dijkstra's algorithm can be considered, though it's unnecessary for unweighted grids like this one. In some variations, dynamic programming may also be used to pre-compute distances, but it's less generalizable. The key insight here is understanding that BFS from buildings minimizes redundant computations, a critical realization that not only improves performance but also demonstrates your ability to refine algorithmic solutions. Great work! In this session, we analyzed and solved the shortest distance from all buildings problem, focusing on BFS and optimization techniques. Remember, understanding time-space trade-offs is essential for tackling real-world scenarios. Thanks for watching, see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!